So first, welcome. I'm showing on the screen both the PowerPoint on the right and the notes on the left. The notes on the left you'll find in your news. Welcome, guys. All right. The notes on the left you'll find in your news, and basically these are notes that go with the PowerPoints. And so as we go along, so if I put them up there, you'll see that they're there. And also I put them up there so I won't forget to say stuff. But maybe this will help you, and maybe it'll help you in the quiz. I don't know. So you're going to have a quiz at the end of not this week, but sometime next week, and it'll be on this chapter and the other chapter. Oh, sorry, the 4 chapters that we will have completed by the end of this week. So last week we did 2 chapters. We're doing 2 chapters today, and that's it. So we're going to talk about computer architecture, and there's some notes here on the side, as it says there. So humans versus computers. Computers follow human instructions. The idea there is computers can't really do anything on their own. They need a human to sort of program them. So the program is introduced to the computer by the programmer. Can computers do anything? This is a test that was actually designed as a mathematical test. There was a mathematician, I can't just remember his name. There's a video there that describes it. Actually, it might be this one. But there was a mathematician in 1928 which came up with this problem, which is called the halting problem. And the idea there is, can a computer do anything? Can a computer know when a program will end? Turing actually came up with a solution to that problem. So Turing is a fellow we met before in the previous lessons. So he actually did this by theory. He said, okay, so if you have one program, program A, which when it is running, program B is not running. And when program A is not running, program B is running. Then if program B was able to call itself, then it would always be running and not running at the same time. And so it was not possible to solve the halting problem, according to Turing. You can read more about that, and there's a video on it. As I said, all of this stuff is backed up by a bunch of videos and stuff like that. Are computers smarter than humans? Computers can do stuff faster than humans, a lot faster than humans, sort of billions of times per second, but they can't do anything that a human couldn't sort of first program them to do. Now, you might say, and as I said, you know, the Terminator movie, when the computer arrives at self-awareness, what we call a singularity, is that possible? I don't know. We're going through process of, we have programming languages that see patterns, are able to connect networks, neural networks. A neural network is an approximation of the way a human brain works. Human brain has a lot of neurons that connect, a lot of neurons. It's billions, trillions, whatever. It's a lot of connections. And so to sort of approximate that in a computer is, I'm not saying it's impossible. I mean, maybe it'll happen. So when it does, who knows what'll happen? But I don't think it's happened yet. If we can make a computer do anything, would we have superpowers? We can make a computer do things really fast, but it makes us feel kind of powerful. I mean, the first time you write your first computer program, you're going to feel powerful. It's like, wow, look at that. Look at that program did for me. In a way which was so fast that I couldn't do any other way except for on a computer. And so that's the superpowers that we think that we have, I suppose. Other problems that sort of come up with it. Can a computer do anything? Almost. This cartoon here is a cartoon by he was a syndicated cartoonist. What I mean by syndicated cartoonist is a number of newspapers, etc., took his cartoons and ran them every day. So if you were living in the 1980s and 90s and you're reading normal business magazines and newspapers, you would see cartoons like this every day. So the guy was quite popular. The thing about Dilbert is, so the cartoons were Dilbert. Dilbert was a IT person that worked in a large company. And so he was always making satirical cartoons. The cartoons are basically making fun of the people who work in large companies doing IT. And so, IT people would look at that and have a laugh at the start of the day. And then they, especially was making fun of bosses. Bosses are usually depicted in here as being kind of stupid or something. Anyway, if that kind of thing makes you laugh, then you might want to read Dilbert cartoons. Anyway, so bosses are not the only people that are kind of stupid. And so we get the idea here. Okay, so the lady with the strange hairstyle, she's what we call a business analyst or a systems analyst. And her job at this point is to go to somebody like they'd be an engineer or something. And the engineer is prayer time already? Or somebody's going? Sorry? Is it now? Should have been an hour ago, right? Does anybody need to go for prayers? All right, okay, so yeah, so the engineer user, the problem with this user is the typical problem users have is that they think they know what they want, but they're not really sure, and they think the IT person should tell them what they want. And yeah, that's the cartoon. And generally what happens is the IT person is trying to build some system for the user, and the user doesn't know what they want, but they'll say some general things. And then now that we have such nice technology and we can build systems so quickly, the IT person will build something quickly and the user will look at, oh yeah, I like that, but would you? And and every time they see them, there's something added to it, right? And so we get this system that just never ends. Anyways, that was fun, Dilbert. Now the links that you'll see in here, some of the links you'll see are a bunch of YouTube videos. I'm not going to go on those because each of those lasts 4 or 5 minutes. The idea of that, and some of them are longer, the idea of that is for you to go and just, I'm kind of like being a librarian here for you, right? Instead of you going and Googling and saying, oh, what can I find out to help me with this class? I'm sort of saying, well, you could look at this. This would help you. I mean, I'm not including it in the lecture, but it would really help you. And actually, it's not really fair for me to say I'm curating this because a lot of this stuff was actually came to me with the slides. So that means that the other classes have it too. And so I'm thinking if the other classes have it too, then it could be on the test. So I would look at it. Yeah, I would say, yeah, this is because there's not really very much on the slides, right, for you to learn. So I would look at these notes that come with the slides. Now, one of the problems that the halting problem I mentioned, but another one of the problems that computers try and solve, is it possible to sort of find the biggest prime number? Or is it possible to find a prime number with 100 zeros on it or something like that? This is a big mathematical problem. And we could sort of, we have a way of doing that. We just take two numbers and divide one by another. That's what a prime number is, right? When the only thing that it's divisible by is another prime number, by the one in itself. Well, we have that. That's a primary prime number. But if you have a secondary prime number, it can be divisible by another prime number and one. So that is a problem that we could put into a computer, and it's very, very hard to solve. Now that's good if you've got a problem with a number, which is very hard to solve. That's good in computing in one way. That's if you wanted to do encryption on a message to somewhere and you wanted to use a key, you could make that key a prime number, which is very hard to find. And so it would be possible to compute it, but it would be so hard to compute it. So it's almost impossible. It would be so hard to compute it that it would be a waste of your time. You'd give up before you did it. That was the idea of it. And so we use that for encryption. And encryption, I'm sure you've come across that. If you do any banking on the internet or anything on the internet where you need to have security, there's going to be some encryption going on. Other place where there's encryption, if you guys are using WhatsApp or Signal or something like that, it'll tell you that it's encrypted end to end. So what that means is before the message goes onto the internet or onto a network, all of the data in it is sort of scrambled, but it's scrambled not in a random, it's scrambled in a non-random way. It's scrambled using a key, which is this very large prime number, right? Which would be hard to compute, but we know what it is, right? And so using that number, we can scramble the data. And then on the other end, we can unscramble the data using that key.
If you're connected to an internet.
Sir?
You can't open the site?
You can't open the site? You got a 404?
Like you're on the Syndicated internet and you try to enter, let's say, Instagram. And you can't enter Instagram on the
all right, yeah. So that's a secured site. The site has been secured so that you have to have a credential to enter it.
So is that called an encryption?
Sir?
There would be encryption involved in it, but basically they've just locked you out. That's not, that specific thing is not encryption. That specific thing is that you have to be authorized. So you have a credential, you have a user and password, and you haven't used that. You just tried to go to the site. Yeah, I think so. Yeah,
Sir?
but there would be encryption involved on everything in the internet. You know that you have encryption when you see on the internet, you'll see HTTPS. You seen that when you go to the banking site, HTTPS? That means that your transaction between you and the bank is encrypted. That means that other people, they might be able to see a bunch of zeros and ones, but they won't be able to see your passwords and stuff like that. Though your passwords is going, you are sending your password to the bank, but it's in an unreadable form because it's been encrypted. So that's what these notes about the RSI are about. I hope I'm in the right place. The RSA,
Sir?
encryption standards that we're talking about, including the semi-prime numbers, as I said, which are going to give you a key that you can use to encrypt your data. 100 decimal digit number is possible using that. And yeah, anyway, so there's some stuff there about that. Now, another problem, which is sort of almost impossible to solve, it referred to here as the traveling salesman problem. The idea of the traveling salesman problem is, imagine a person that had to go and visit a bunch of cities in a country like United States, where there's cities just like every 100 miles there's a city, right? And maybe this traveling salesman had to go and visit all of these cities, but doesn't want to waste his time or her time by visiting the same city twice. And wants to visit all the cities using as least amount of gasoline and as least amount of time as possible, but not visit any place twice. So that's a problem which is kind of hard to solve. The more cities you get, you're likely to have to travel through one city more than once. Yeah, so there's we could come up with it wouldn't be hard to just, if the problem was just to visit all the cities, that's, yeah, no problem. But the problem is not just to visit all the cities, but to visit all the cities only once and using as least amount of gasoline as possible. And so that's what makes it sort of difficult. And those kind of problems, we don't actually, it's typical that we don't get the exact answer very easily. What we get is the best approximation. So we get the shortest possible route. So there's a bunch of stuff there, links that were, I think those are just going to take you to Wikipedia or something. Well, let's see where those links take you. Yeah, so Wikipedia, and it's going to explain to you what that term means. So we got a few terms there that if you're interested, you can go and get a bit of background on them, what they mean. Hopefully those could help.
Sir?
Somebody's talking to me. I just
Yes,
added this course and I don't know what I missed. All right, I'll talk to you a bit about that at the end of the lesson. Okay.
Okay, thank you. Thank you, sir.
Well, let's talk about hardware. That's the next sort of slide here. And I hope you can see all the different components that make up your typical desktop computer, or your computer that's sitting underneath your desk, but we call it a desktop. So if we started at the most important, or the heart or the brain of the computer, I guess you'd say, we often refer to it as brain, that would be the CPU, the central processing unit. Central processing unit is kind of like that rectangle there. Notice that the central processing unit has a fan that sits on it. That's a heat sink fan. The idea is to remove as much heat from the CPU as possible. It does produce a lot of heat. And the more powerful the CPU, the more heat. And the more heat, the problem of the computer, we need to get that heat out. So we use a fan to get the heat out of the CPU directly. And then we're going to have other fans in the box to get heat out of the box. And then we're going to have an air-conditioned room. If I took you down to what we call the entry point here at the college, there's a room down there in building 3, which is our entry point. That's where we call it the entry point because that's where Arito provides us with our connection by fiber to the internet. There we have all of our main servers, and the room is air conditioned. If you go there, you need to take a jacket. It's always in the teens. It's like 15, 18 degrees. Now they do that because there's so much heat coming out of those computers, right? The computers will fail if they get hot, and so they're using a lot of heat. If you went there, you'd also find that in the room next door, they got diesel generators. The diesel generators are there as backup power in case of the electrical power that's provided to us by, what is it, Kara? If that fails, then they generators start up, because we don't want those air conditioners to stop, and we don't want those computers to fail, right? And so that's quite an important sort of thing there, getting that heat out. Okay, so this thing there that looks like a big rectangle, seems like it might be an important thing. It is. It's called the main board. Sometimes we used to refer to it as the motherboard. The main board or the motherboard has a place where the CPU slots into a socket. And so that socket has connections that go to other parts of the motherboard. And those connections are called buses. So we have a bus that goes to the memory. We have a bus that goes to other components. So the main bus going down here that we can go to other components that are good. These slots will allow you to add components to it. There's a bunch of other things in there. Now, one of those slots, if you didn't have it built into the motherboard, you'd have a Vga card. And you might notice that Vga card also has a fan on it. That's because that Vga card has a processor on it. So the processor on your Vga card, especially if you've got a gaming machine, it's going to be a powerful processor. It's actually as powerful as a computer would have been a while ago, right? And because you need a lot of processing power if you're going to play games, which is, millions of calculations every second to get the pixels to move in the right place so that you don't lag, so that you don't lose, right? If you lag in a computer game, you lose, right? Snooze, you lose. And so you got to have a card that works quickly so that you can do that. Some other things that we plug into these slots over here on the far right are the DRAM slots. That's your random access memory, which gives you your fast, expensive memory outside the CPU. The CPU actually has some memory on it itself. And then there's some other memory, which we call secondary memory, which is going to be our hard drive. Here it's called a hard disk. I'm going to call it a hard drive because hard disk is kind of what I'd call legacy hardware. Legacy meaning that it's becoming obsolete, meaning that it's being replaced by something which is more modern. And, sorry? Very good. By the SSD. So your hard disk is being replaced by the SSD. That's your more modern technology. It's a faster technology. What I mean by faster is your transfer of the data from the SSD to the memory, to RAM or into the mother. It's going to go to RAM. It's going to be faster than the old moving parts hard drive. Sorry? I do. I was using the 8-inch floppy disk. And then after that came the 5.5-inch floppy disk. But yeah, and then after that came the 3.5-inch floppy disk with a hard plastic. Yeah, so only old people and you know about it. Yeah. There was a 5.5-inch that came out in the 80s, but before that, in the maybe 80s and 70s, there was an 8-inch floppy disk, and before that, they used to just use tapes that kind of look like your VCR or your old VGA video graphics adapter. Yes. So. All right. So actually, all of that is over here, and I'm sorry that if I skipped it. But you'll see here we talk about the CPU and the GPU, the graphics processor. Should be there, the cards. Yeah, there's a VGA card, video graphics array, not adapter. And so all of that is in the notes. So I'm sorry I didn't mention it. Anything I miss, please have a look in the notes to catch up on it. I do encourage you to do that because it might show up in the. There's a bunch of other sort of add-on things. This reader, all in all, I wish I had that in my computer on my laptop because I don't, because I actually had to go and buy something separate so I could read my cards that I took out of my mobile phone. Okay, so we are going to spend this week in our tutorial session. We're going to learn about binary, hexadecimal, decimal conversions, what these numbers mean. So binary means you only have two numbers, 0 and 1. And so 0 and 1 means you can have two states, on, off, yes, no, true, false. Something like that. That's our 0 and 1. But if you put two together, then you can have four states because you'd have 0, 0, 0, 1, 1, 1, 1, 0, right? So that's four different ways of organizing two bits together. And so this would be referred to as 2 to the 2. 2 to the 2 is 4 ways. This would be referred to as 2 to the 1. 2 to the 1 is 2. There's 2 different ways. This is 4. 2 to the 2 is 4. 2 to the 1 is 2. If you had 3 bits together, it would be 2 to the 3 different ways. 2 to the 3 is
8.
8. 2 to the 3, because it's 2 to the 3 is this. 2 to the 3, which is equal to 2 times 2 times 2, which is 8. And so 2 to the 4 would be, so this is 8, and this is 16, I heard somebody say, yes. And 2 to the 5 would be 32, and 2 to the 6 would be 64. You've probably heard these numbers. These are the numbers we use in computing all the time, because everything is based on this binary. All right, so if you had 3 bits, you'd have 2 to the 3 states, 8. If you had 4 bits, you could have 16 different states.
So when you say different states, you mean 0 and 1?
I mean, on, off, you know, sort of between on.
I mean, like 16 different numbers?
Yes, 16 different numbers between 0 and 15.
Okay.
Yes, yes, that's exactly what it means. 16 different numbers. Okay, so that's what binary is. We start off with 2 numbers, but we can arrange them beside each other to get lots of other numbers. And not just numbers, we can arrange them to represent symbols, etc. Have I got, okay, so the next bit there is about how does a program work with the fetch and decode and execute. We're going to talk about that a little bit now, I think. So yeah, the program is stored in the RAM. Now, I hope you remember in the hardware picture, the RAM was separate from the CPU. So the RAM has the program in it. The CPU has 2 parts to it, at least. Well, it actually has 3. It has more, because it has the control unit. It has the arithmetic logic unit. It has registers, and it has cache. Registers and cache are memory that are in the CPU. But anyways, the CPU is going to fetch from the memory, from the random access memory, an instruction. Now, that instruction then has to be decoded. That will also happen in the CPU. Once the instruction is decoded, part of that would be the decoded instruction may require some data to go with it, in which case that data will be requested by the control unit as well. So the data at decode time is going to come in, and then the next step is going to execute the instruction. Once the instruction is executed, there's probably going to be some result, and that result will end up being put into the memory. Now, in the meantime, any intermittent, or how would I say, between results will be stored in registers in the CPU. So the CPU actually has some little memory space, which is called a register. The control unit controls the entire cycle. Now, we've got these 2 different architectures, and that's what these notes here are about, and that's what this diagram is about. There's a video about it. Oh, if you Googled it, if you Google Van Neumann versus Harvard, you'll find 20 different videos made by lots of different people. But I think I've given you some, if you look, I've given you a link to one or 2. There's probably one there or something. So what do I want to say about that? The von Neumann architecture was earlier. This was developed by von Neumann in 1940s. After that, the Harvard architecture came. The Harvard architecture, if you look at it, the diagram looks bigger because there's a little bit more happening there. So what do I mean by what's happening? You'll notice that the same bus here is going to the code memory and the data memory, same bus. Whereas in the Harvard architecture, we have a different bus going to the code memory as goes to the data memory. So we got 2 separate buses going there. And so the Harvard architecture is better for some things, and the Van Neumann architecture is actually a little bit more flexible. The Van Neumann architecture is used in your PCs. And the Harvard architecture is used for more special purpose CPUs, like as found in a mobile phone or a special, like in your car.
So I have a question. Now, does the CPU, the first one, the one here, does it make the data memory slower when it goes to the code memory first?
I think the fact that, good point. I think the fact that it's using the same data bus for more than one thing, I think that means that it's going to be a little slower because the data bus could be more busy.
Because I'm thinking of it like Do you know the series circuit and the parallel circuit in the physics?
Yeah.
Electricity. I'm thinking of it the same thing.
You're thinking that the Harvard is a bit more parallel and the Van Neumann is a bit more serial. Yeah, okay, I think that's a good way of looking at it. And I think that you could say that your Harvard is probably going to be a little faster for that reason. It's interesting you say the parallel because the original printer cables that we used to use on our first computers would connect to a thing we called the COM3 port, and the COM3 port was a serial port, and that was a slow printer port. And then they developed a printer port, which is a parallel printer port with a special ribbon to do it, and that was our faster printers back in the 80s. Good point. Thanks for bringing that up, Omar. The fetch, decode, execute cycle. We got some notes that represent that here, but what I want you to notice is the main memory, which is outside of the CPU, and then these units here, which are represented as being inside the CPU, outside the CPU. So an instruction is going to be brought from the main memory. So we're going to start here with this arrow. The instruction is going to be brought from the main memory into the control or by the control unit of the CPU. And that's going to be a fetch. So we're going to have a fetch, which is going to bring that instruction in. Then it's going to decode that instruction. Okay, and as it decodes the instruction, it's going to request any data. It's going to be request the data at that point there in the execution cycle. The registers are going to sort of pass those between. Then after it's decoded, it's getting that data as mentioned, and then it's going to execute. And then after it's finished executing, there may be some things to write to registers, but if it's finished, it will pass that out to the main memory, wherever it's going to go after that. So there's some notes on the side after that. The next sort of slide regarding that is kind of a lighthearted thing, I suppose. And I guess the idea is that, I don't know if you guys are sort of relate to the Power Rangers or whatever they were. But the idea is that you could have a single sort of superhuman that could do all the things. Is that right? Did they come together? Yeah. That's it. Yeah, they came together to make a single sort of superpower, right? And so
each part is controlled by one member.
there you go. So our processor is kind of like that.
That is the leader.
Yeah. So fetch, decode, execute, memory, and write back all happens in one single superstar. All right. And an example of that. Again, there's a video there that sort of represents that. So like you were saying, Omar, the Harvard is going to be faster. And no doubt, partly because of those things that we talked about. And there's some more stuff about how that happens. I think I repeated this. Anyways, the last one there is about can we imagine cooking, and what does that got to do with the fetch, decode, execute cycle? Oh, all right. So imagine you went to the internet and you did Google and you said, okay, I want a recipe for so and so. And then the recipe came. That would be fetching. As we went to the internet, we fetched the instructions for how to cook something. That's a fetch. All right. Then we went and we decoded. And after we decoded we were thinking about it, right? Okay, so I'm going to need this, and I'm going to need that, and I'm going to need that. So that's going to be our decoding. And once we've decoded it, we're going to go and get the stuff that we need. So that's moving into the execution cycle, where we're getting our data, except instead of getting data, we're getting onions and eggs and things like that. We're getting all of that, and then we're actually making it happen, cooking it. Yeah, execute. And that brings us to the end of lecture 3. So what I'm going to do now is maybe you have some questions or whatever, but I'm going to stop the recording. And I'm going to take like 5 minutes and then get the next lecture up. The next lecture is a little bit shorter. Okay. That's good for me. I don't know about you guys, but